Hello. This video is about two designs that I made way back, I would say in the in the second half of the 1980s. The first one was, I'm guessing, around 1987 or so. I can find that out more accurately. And the other one here was designed around 1989 or late 1988. This is the prototype of a project that I developed for Electronic Musician magazine. And this is the prototype, so it's not got a very finished appearance. It was called the Pocket MIDI Controller. This other one was supposed to be a follow-up and possibly turned into a commercial product. But this one wouldn't have been very easily built as a kit or a build-it article, which I think is why it didn't really make it to the magazine. This is called the Son of Pocket MIDI Controller. There was a follow-up one which was definitely intended to be a production article, which was called the Grandson of Pocket MIDI Controller. At the time I was into Godzilla movies, what can I say? Anyway, I thought it would be interesting now so many years later to just do an overview of these two designs, in case anybody's interested in that type of thing or nostalgia from the early MIDI era. The Pocket MIDI Controller was designed to be a very simple, easily built device you could carry around just to act as a diagnostic tool on the stage or in the studio. And also, it could be useful going into a store to check out pieces of equipment by sending certain select MIDI messages. Primarily, its usefulness was to determine whether a particular setup was functioning or not and where the problem was. For example, if a piece of MIDI equipment isn't putting out, is it the controller that's sending it? Is it the cable? Is it the setup of the MIDI equipment? That type of thing. And this was designed to be, in the smallest, simplest package possible, a device that could send out known MIDI messages. So it has a MIDI output cable, a short length of cord. It could be wrapped up and put in your pocket. It runs off of a 9-volt battery. The case didn't have quite enough room for the battery inside, so I carved the hole out so it would just barely fit. There's a power switch. This is a volume switch, so it would send the MIDI messages at one of 3 different volume codes or amplitude codes. And this was a pitch selector switch, so it could send a low pitched, a medium range pitch, or a high pitch. And then it has a momentary push button which acts like a key, so it sends the message when it's down and cancels the message or gives a MIDI off when the button is released. Opening the case of the prototype, you see it's just a simple SP-ST switch and a couple of SP-DT toggle switches and a momentary push button. Getting the battery out of the way, it has 7 4000 series logic chips, a crystal, a few diodes, a few resistors, a transistor, a couple capacitors. Not really much else to it. Very simple design. And I'll go through the magazine article separately, but the idea was you could build this in here, and if you didn't put all the chips in sockets, I had them in sockets because this was the prototype and I expected to take them in and out a few times. If you didn't put the chips in sockets, then there actually was room inside the case to put the 9-volt battery, but putting them on sockets raised it up too much, and that's why I kind of hacked out a hole in the case. But if you were to build this off the magazine article, you wouldn't probably have them in sockets. With the Pocket MIDI Controller plugged into the MIDI input of my digital piano, it's the only piece of MIDI equipment I still have, having pretty much gotten out of this area many years ago, but I did keep these prototypes just for nostalgia, if nothing else. Anyway, so I've got the keyboard set up in keyboard or piano mode, and turning the Pocket MIDI controller on and setting it to the lowest pitch. So I'm playing a high pitch there. And like I said, this is the volume switch. It was in the lowest volume position. So that worked pretty well. Put it back to the medium volume, and here's the high pitch. These switches are old Radio Shack switches, and they're not very good. They're kind of getting gummy in their old age. It depends where the sustain and decay envelope is currently going on in this keyboard versus when I send the MIDI off message or the note off message. It depends how it reacts according to those factors. Like if I do that, it doesn't give a quick cut off, but if I go, whoops, it cuts off a little quicker. But that's the piano, not the MIDI controller. So again, low, medium, high, soft, medium, high volume. So the Pocket MIDI controller was actually a follow-on article to an earlier one called Build a MIDI Switcher, which was originally published in Electronic Musician in their August 1987 edition. Here's the letter from the office manager. This is actually my complimentary copy that they sent me because they were going to publish the article. MIDI switcher primer. Where is it? Primer. So in this one I was trying to show how simple it was to make a MIDI switcher without using a microprocessor or anything more complicated than just simple ANDs and OR gates and appropriate opto-isolators and transistors. Very simple stuff. And I showed a simple switch there with an AND and a couple ORs and an inverter. I showed the basic lineup of a MIDI current loop and talked about suitable power supplies and how to start with a patch diagram to expand it into a workable schematic, and showed the pinouts of the appropriate ICs, and that was quite well received. So was this issue from the next year, the September 1988 edition of Electronic Musician, where under the Do-It-Yourself column was Build the Pocket MIDI Controller. And there's the letters from the editors saying they'd accepted the article, and the proof diagrams for my corrections and anything else I might needed to make. So you can see the rough layups here with their notes showing how they plan to lay it out. You know, there's going to be a Yamaha ad on the next page, page 51, that type of thing. And so here was the article, the Pocket MIDI Controller, on page 50. And their mock-up for the magazine was in a similar box to the one I built as a prototype, but they didn't lay out the switches in the same way. doesn't really matter. I never did know if they actually made a working one as a proof of concept on their end, you know, before endorsing it in their pages, or if they just made a mock-up for the purposes of a photo. I presume they actually built it. The editor, who was Craig Anderton in those days, was pretty careful, and he was knowledgeable in electronics and MIDI, so he probably built it as a proof of concept before publishing. Anyway, so talked about how a MIDI signal is constructed out of various serial bits, and it showed the schematic. The schematic of the Pocket MIDI Controller was just a crystal oscillator built around a couple of NAND gates, capacitors, and resistors, and then it went into a 64 divider to generate a 31.250 kilohertz square wave from a conventional 2 megahertz crystal. And there were 4 8-bit shift registers all connected in series, with a 1 shifted in at the very beginning, and 1 is the normal null state of the signal. So if you just let it run, it would fill itself with zeros, logical ones, which is a MIDI 0, so nothing would come of it. Essentially, it would be like sending out a continuous stream of nulls. And then the final output of the shift register went into a transistor, which was a current sink and would pull against this pull-up resistor through whatever MIDI device was connected out here. And then there was this controller here, which 3-position switch off in the center, energized to either side. And the rest of the logic here was really just how to get a useful bit pattern in. Now the bit pattern overflows the 8 bits because there's start and stop bits, but you can get the entire message spread over 4 8-bit shift registers. And I actually diagrammed it here. You can see where the first 2 bits are just a space bit, and then the 8-bit velocity byte starts here and spans over to the next chip, and then there's a space start bit pair here, taking those 2 pins, and then the 8-bit pitch byte, another 2-bit start-stop pair, an 8-bit message/channel byte, and then another 2-bit start-stop pair. So that's how it all fit in there. And for the velocity, which would be the loudness essentially, how loud the MIDI device should play the note, it was all just worked out to whatever bit pattern I could control as simply as possible. And similarly with the pitch byte, a single switch through some inversion and diode resistor logic came up with the appropriate pair there that would give suitable low, medium, and high pitches. And then finally the key was a normally open pull up against a pull down resistor, and you either inverted it or inverted it twice, so essentially not inverted, and then a couple of monostable RCs, either of which could feed into this. So every time you push the key or release the key, you'd get a 100 microsecond pulse out at this point, and that's what caused all of the shift registers to load in the data that was coming down here. Some are permanently pulled up, some are permanently pulled down, and then there's the ones that vary according to the switches. So that's how the circuit worked. Had a parts list along with all the ads. There was some description text. There were diagrams showing how the bit patterns worked out. You have to send the MIDI message byte and the MIDI channel. Then you have to send the pitch bytes, and this shows the way it looks for the low, medium, and high. And then the same thing for the MIDI velocity byte, loud, medium, and soft, showing how the patterns work out. And the transistor and IC pinout diagrams. some construction information, suggestions on how to modify the circuit, and then it continued to page 101, as magazines often do. Yeah, it came over here, and then just a little bit at the end to close it out. I'd suggested how to make this more performance ready by putting in debounce circuits and things like that, which the Pocket MIDI controller did not have. Anyway, so that was the Pocket MIDI controller. So here's the son of Pocket MIDI controller. This was fit into a PackTech box, and it used the, I believe it was 3M process for making your own front panels, which they've discontinued, sadly. I don't know of any good substitute for it. But I actually had a membrane switch, a 4x4 membrane switch stuck down onto the recessed front of the PackTech box, and then a filler piece of plastic of the same thickness. You can just see the seam there, glued down to make up the thickness. Fairly reasonably professional proof of concept front panel. And PSR was a company I had at that time for doing consulting work, and so I just put that on there. So what does this have? It's got the keypad, it's got 4 LEDs plus a power LED, power jack on the left side, 2 MIDI jacks, an audio I/O jack, a couple of trim pots that can be accessed there. There's a slide switch, 4-position slide switch, and then there's 2 toggle switches that are recessed, so they're barely sticking out. The slide switch was something that was added later. It was a firmware upgrade to this prototype, so there's no legends on the front describing what it does. But the other 2 were designed to be there from the get-go, and they are the volume and power switch. To avoid having knobs sticking out, everything was done with switches, so to keep a low profile, put it in a pocket, you wouldn't get it banged up. So basically you just had power on and off and volume low and high, and then you could adjust how high the high was and how low the low was with the trim pots. The slide switch, as I recall, was there to change the timbre of the tones this thing would play a little bit. So you got your MIDI in and out, and basically this device could do all sorts of handy musician things. The simplest thing it could do was act as a tuner. So if I turn the power on, get the power on light, and you had all the pitches of an octave. I don't have the case screwed down tightly and it's kind of vibrating. And something is let loose with the glue that held the speaker in place, so it's buzzing. It didn't used to buzz. There it goes. And there's an octave button here, which I can push, and then you continue with the next octave. Push it again. And then back to the original octave. Tone button here would cause it to produce a constant tone. Whatever button you pushed, it would just hold that. Let's see if I can turn the volume down a little bit. That's better. So it would just hold whatever note you got. You could use it to tune other instruments, for example. Push the tone button again. And it would automatically play either A, B flat, or C without pushing any button. So just toggling it over and over would go A, B flat, and C. And then hold would release it. Hold was also used So I actually had it backwards. The hold button is the one that makes it hold any note you push, where tone plays a specific one of 3 notes, and hold releases it. The LEDs also indicate the MIDI channel of an incoming MIDI message, so you know what channel it's being transmitted on. It's in binary, but MIDI messages are on channels 0 through 15. Or I'm sorry, they're on 1 through 16, and the binary can only show 0 through 15, so that's why it says MIDI channel -1. So whatever the real MIDI channel is, the binary pattern will indicate that value -1. But without a better display, that's the way it worked. So let's see here if I can demonstrate the slide switch on the side. I'm not sure that's actually implemented. The slide switch doesn't seem to be doing anything now, and I honestly can't remember anymore if the code is in the microprocessor or not. Anyway, so other things this would do is it could be used as a MIDI tone generator. So plugging in a MIDI source, it would play whatever pitch was requested within a 3-octave range over its internal speaker. And then any pitch you've selected here would go out the MIDI jack and would play that pitch on the MIDI device you were connected to. It also had a single audio I/O jack, which could be both an input and an output. If you're driving it from a low impedance device, which most outputs are, it would override the internal circuitry and would just cause the little speaker and amplifier in here to be used almost like a tiny little guitar amplifier. And you could use it as a practice amplifier, for example, you know, just a tiny little practice amp, or to test out audio cables, that type of thing. Everything from microphones and so on, as long as they were low impedance. If they were high impedance, it would not properly override the internal signal generation circuitry. Otherwise, if you plugged a high impedance or medium to high impedance inputs cable into this, going into another amplifier, for example, then whatever tones were played here would also come out that jack and could go into a bigger amplifier. So you could use this like a tuning device, a tuner, a pitch pipe, if you will, an audio amplifier, a MIDI tester, a small MIDI sound generator, or a MIDI controller. So pretty much all the things that the Pocket MIDI controller did, except that you could not specify the velocity of the signal. It was always the same thing. So for demonstration purposes, I have my electronic keyboard over there, and with the MIDI cables both in and out coming over to where I'm at. And now I'm plugged into the MIDI output of this device. And let's see if I can do this. So you can see how it's able to act as a MIDI controller. Now, one other thing I forgot to mention about this is it's also got a Baroque button, which just shifts it by a half step. So if you're using it as a tuner, for example, it's primarily useful as a tuner, since Baroque tuning is often considered to be approximately a half step away from modern tuning. And this could be used as a pitch pipe, and I thought, well, some groups that are doing early music might want to tune at a slightly different pitch standard than modern pitch standard. So I just put that on there to use up the last button. But you can see here, if I push down a hold, so there's a B. if I go Baroque, it's lower. If I take Baroque mode off, it goes back up by a half step. So that's the MIDI output function. If I plug in the MIDI input, you can see on here it's ticking, and that's because this particular keyboard is trying to put out like a metronome signal on one of the channels, and this MIDI controller does not have a channel filter. It responds to all channels pretty much. So let's see if I can make this work. Oops. So it's a little bit annoying to have that ticking going on, but let's see. There you can hear. You can hear the keyboard playing. I'm going to turn its own volume off, so we're just hearing the MIDI controller. It just keeps rolling over. There's obviously some sort of a fault in the firmware here where it gets lost sometimes when it's acting as a MIDI diagnostic device. And that and the fact the cable keeps wanting to pull it off the top of the keyboard here. But you can see so it does respond to the MIDI signals from the keyboard. I don't really know for sure why it's ticking like that. With other devices I had back in the 80s when I built this, it did not produce that ticking noise, so I think it's something that this particular Kawaii keyboard is putting out that the firmware was not designed to deal with. But whatever it is, it doesn't keep doing it. When I turn the keyboard off, it stops. And then when I turn it back on, it resumes. So, what's inside this puppy? The speaker's on the back and comes out through these holes. It runs on a standard 9-volt battery. These PackTac boxes are really nice. I use these on a lot of designs for portable industrial equipment I was doing as a consultant back in the 80s. I really used the same concept. I based almost all those on this 4x4 matrix and then some LEDs, but the connectors would be different and so on. So anyway, I've mentioned it has a supply jack. If you plug in a wall wart to that, it disconnects the internal battery. So here's what it looks like inside. Got your power jack, the sort of kludged in, epoxied in 4-position switch, a little daughter circuit board which held the 2 toggle switches so their tips would only just barely stick out through the side of the case. And that's again your volume switch and your power switch. The battery compartment, the 1/4-inch audio I/O jack, the 2 MIDI jacks, and then the circuit board. And here's where the ribbon cable from the 4x4 keyboard matrix comes through a slot in the case and plugs in here. There aren't a lot of parts on the board. There are 3, you can see one kind of through the ribbon cable here. 1, 2, 3 voltage regulator ICs, low power ones, each with their own tantalum capacitor. And then this is the transistor for the MIDI output current sync. And the reason I did this is because to get all the parts to fit, I had to mount components in this area, but the battery compartment comes right down across the top of the circuit board from here to here. So you can see there's taller components here, but everything here has to be essentially flush with the circuit board. And that's why I mounted these parts on the back of the board, and their thickness is accommodated by having holes in the circuit board into which the bodies of the components fit. I thought that was kind of clever at the time. I still kind of do. It uses an Intel 8031 microcontroller, although this one may be second sourced by another company. It doesn't seem to have the Intel indicator on it or logo. But the 8031 probably was second sourced. I don't know who made this one. Is that Schematic? I'm not sure. Anyway, so that was the microcontroller. Nowadays you'd use a, Atmel or one of the other, a PIC chip or something to do the same thing. But in those days I was doing consulting work using the 8031 series, and I was familiar with it, so I used it. There's a 74 340 or 374 and a 373, and those are just octal latch chips. Those essentially provide the I/O, and some of the I/O comes directly off of the pins on this chip, and the rest is derived from these chips. And then you've got your EEPROM over here with the firmware in it, and the rest, this is your opto coupler, which is for the MIDI input, and then over here is a LM386, which is a small low power audio amplifier chip, and it has a few support components on the board. But and there's your trim pots for setting the low and high volume levels that are selected by the volume selector switch. So really not that much on the board. There was obviously 4 pins on a port of this controller which were not used, and they came to holes on the board to allow for future expansion, and at some point it was decided to wire those out to this switch so that it could be used for something. And as I recall, the idea was that it would be used as a to select from different waveforms when this is being used in like tuner mode to produce different timbres of notes. As I pointed out, some of the components are mounted on the back of the board just because there's not enough room to have them on the top of the board. And there's also an electrolytic capacitor which fits into a slot there. Again, the 3 voltage regulator ICs and their associated tantalum capacitors, the output transistor, and there's also in the same area a couple of diodes, some filter or decoupling capacitors, and the decoupling capacitors for the logic chips are mounted on the back of the board. There's your LEDs and another resistor, but most everything fit on the front. There's the holes in the case. This circuit board actually just sort of wedges in place, but originally I was going to mount it with some studs, but there was nothing in the PackTech box to support studs in those positions, so in the end it just got epoxy glued in place. I had a small tab of glue there. Actually, I may have used CA glue for the prototype, just a dab to keep it wedged in place. I had to break that out to open this up for the purposes of this little documentary. But that's the overview of the physical side of this. So here's the schematic of the son of Pocket MIDI Controller. The same schematic was used for a couple, 2 or 3 different ventures trying to find companies that would actually want to build this, but it never came to anything. There wasn't really a competing commercial product or anything, but I wasn't also trying very hard. And I should also mention that one of my best friends who was doing some of the consulting work with me in those days was really instrumental in writing the microprocessor firmware. I could write 8031 code. I'd done it at my regular job when I wasn't consulting, but we often had a collaborative relationship where my friend would do the heavier coding, and I would do the circuit design and the printed circuit board design, and do all the documentation, write the specification and that kind of stuff, and he would do the bulk of the programming development, and that was the case here. I don't remember if he or I made the schematic, probably me, but who knows anymore. Anyway, this is a sort of a paste up here because it was for the prototype and things were not completely settled yet, but this is the layout. You've got your 4x4 keypad, and it's just a matrix, 4 rows and 4 columns. So this one 8-bit port on the 8031 was used to scan that keyboard, and this is the remaining pins that were left over, the interrupt 0 and 1 and the T0 and T1 pins, and those are the ones that were for future use. And we thought we might eventually expand this to have a small LCD display, but as I pointed out on this particular one, we thought we would wire that out to the 4-position slide switch and use it for something, but I don't believe we implemented that in firmware, at least not the firmware I have on here. This is your power-up reset circuit. This is your crystal oscillator with its supporting capacitors. The 8031 basically has 3 8-bit user ports on it. Already described what this one's doing. This one was sort of used as an 8-bit general purpose bus. It was latched into the 74374, which is an octal latch going that direction, so the data in and the Q outputs, and that was controlled by the clock signal, which in turn came from the write signal of the 8031. So when it thought it was writing a word of an 8-bit word to memory, it was actually writing it to this octal latch, and then that output could either go to a future LCD display, or on this version it was used to drive the LEDs. At least 3 bits of it were used, or 4 bits were used to drive the 4 LEDs, and the other 4 bits came down here and made into this real cheap and dirty analog or digital to analog converter. So you had a weighted resistor adder circuit here, and depending on which bits were turned on and off, you'd feed more current into this junction here, and that in turn was capacitively coupled out to the jack. So that's how this thing generated its pitches. It had a waveform table in the EEPROM, and the software would play the waveform back at different speeds to generate the semi-sinusoidal waveform. It was, as I recall, it had a bit of an edge to it for some higher harmonics, but it was essentially sinusoidal. Let's see what else. So there's that. Here's the identifications of the LEDs. MIDI channel and binary -1 for the actual number, or it could be a function. And then this 8-bit bus could also be coupled into the 74373. Once again, this is used for data going in this direction, but in this instance it's used for producing the lower order addresses to the EEPROM. So because there's not an actual address or data bus on the 8031, you could make the ports act sort of like that, but they would put out a address 8 bits at a time, which was not uncommon for microcontrollers and some microprocessors. So it would put out the lower order 8 bits of address. They'd be strobed through the gate pin here, which was controlled by the ALE/P output of the 8031, and that would gate that data in here, and then it would be presented to the lower order 8 bits of the address on the 27 16 EEPROM chip. The higher order bits, A8 through A10, then came from 3 pins on the next user port, the remaining pins of which were unused on this design. And then the outputs of the EEPROM went onto that same 8-bit bus and strobed in by the output enable, which, if I follow that around, went from the PSEN signal of the 8031. So really a simple circuit in that regard. So let's go back to the analog circuit. Already described what happens when it's working as a D to A, and normally that would override anything else that was going on, and that signal could be presented to an external amplifier through the capacitive coupling here, or it could be capacitively coupled into these 2 trim pots, which set the low volume and the high volume, and then you'd switch that with the volume switch and go into the LM386 amplifier with its requisite number of a minimum number of components, capacitively coupled 8-ohm speaker, and if you were going to use this in the other direction, put signals into it, these are all fairly high impedance values here. So if you put a signal into here from a low impedance output device, it would override whatever was coming from here and double capacitively couple, if you will, bang to the amplifier and be amplified. And that actually worked fairly well. Of course, ideally you would set this up so the D to A was not trying to generate any signal, so you weren't really competing. But if you did, chances are this would win anyway, just the impedances were set up that way. So what else do we have on here? Required a 200 milliamp 9-volt AC adapter or wall wart, and there's your battery, 9-volt battery, and if you plugged in the wall adapter, it would disconnect the battery and apply power directly to the power switch, which then went into 3 voltage regulators. They're all 78 LO5s. The reason that they're split up this way is just because they couldn't handle all the power for everything with one device, and it was thought to be a good way to isolate one circuit from another to avoid noise coupling and so on. So one regulator is used only for the microprocessor or the microcontroller. The other one's used for all of the other ICs on the circuit board. Oh, there's your power LED, by the way. And then, in case a LCD display was going to be used in the future, there was that additional 78 LO5 to power that, but we never came up with that version of the device. Now, I mentioned earlier that there was supposed to be the grandson of Pocket MIDI Controller, and it would have used the same circuit board as this, but it would have had the LCD display instead of the LEDs, and it would have had more information on it, and there would have been a couple additional modes that you could have put it into to accomplish more features. Anyway, so there's that, and then finally, here's the MIDI input. In case you're not aware, a MIDI signal is really just a current loop, a digital current loop. So it's either on or off, but it's pumping current through a loop of wire from the transmitting device to the receiving device, and simply whether there's current or not current indicates a binary 0 or 1, not necessarily respectively to that. But this is the conventional circuit. You've got a limiting resistor, and then an optocoupler with an LED, of course, being an optocoupler. And then there is a diode in case it was backwards, it wouldn't damage this. But essentially you're turning this LED and the optocoupler on and off with the current loop signal coming from the MIDI device that's hooked into here. And then the transistor output of the optocoupler is pulled high through a resistor, and whether the transistor output's on or off dictates whether this signal is pulled high or if it's pulled low through the optocoupler. So you end up with a serial binary signal going into the RxD input of the internal UART on the 8031. And the 8031 did have that internal UART, so that made it simpler to decipher the incoming serial signal, or the incoming serial data. And then the TXD, or transmit output of the internal UART, went down here, went through that one PNP transistor, and that directly drives the output jack, the MIDI output jack. You've got your V+, goes through a current limiting resistor. It goes out on pin 4, and if it went to another device, it would have a similar circuit to this, where it would come in on pin 4, go through the optocoupler of that device, come back out on pin 5, go back through the cable, and return to this device on pin 5, which then would either go to ground or be open and not go to ground. So that's how the current loop would be controlled and received. And I don't think there's really anything else to this. Relatively simple circuit and functional firmware. Not bad for a prototype stage design that never went any further. But having said that, for many years in Chicago, I mean, we're talking, I don't know, probably the late 80s, the last couple years of the 80s, all of the 90s and into the early 2000s, I used this group as a tuner for some choral groups that I was in the city of Chicago. And this was the device we tuned with. And some of them were early music groups, and they appreciated the fact that I could use the lower pitch that was called Baroque pitch on this, since that was pretty close to what they wanted to do anyway, and you didn't have to remember to step it down by a half step. So that actually did come in useful. The fact that it could make a pretty loud tone allowed a whole group to hear it, where a pitch pipe maybe wouldn't be loud enough. So this prototype actually got used a lot for quite a long time, and then when my association with those groups ended and other devices came around that were smaller and lighter, this just went in a box, and it's really only recently that I've taken out and dusted it off and decided to do this video. So between the Pocket MIDI Controller and the Son of Pocket MIDI Controller, I think there's only one more thing to do. Pocket MIDI Controller feeding the Son of Pocket MIDI Controller. And I don't have the cover battened down here, so it's going to buzz like crazy probably. But let's put both the switches in the low position. This switch is real bouncy now. And then I'll go up to the middle position here. So that's a low pitch, medium pitch, high pitch. And you can see they're not octaves. As I mentioned before, the pattern was whatever I could generate with the fewest components, so it didn't work out to be a nice even octave. And then here's your velocity. Of course, this doesn't respond to velocity, but we did hear it working on the digital keyboard. Anyway, they do feed each other pretty well. This didn't used to have this problem, but it's so bouncy now that when I push it, it can send 2 or 3 signals instead of 1, and depending whether that lands with a on or off is why it doesn't always stop playing. Anyway, functional. Hope you found this interesting.